All right, welcome back, everybody. Did you like the thumbnail? Those are supposed to be pigeons, because today we're talking about the pigeonhole principle, and I'm going to make this real simple. We're going to just go over the definition. We're going to look at two examples applying the definition of the pigeonhole principle, and that'll be it. And hopefully we'll have a good understanding of this principle. So here's our definition. Let A and B be finite sets, and let f be a function mapping A to B. Now, if the size of A is greater than the size of B, then f is not one-to-one. And if the size of A is less than the size of B, then f is not onto. Now, if you have a good understanding of what onto and one-to-one mean, then these facts should seem pretty obvious to you, right? But why do they actually matter? How are we going to apply this, right? Well, let's think about this, for example. Imagine you have a room, right? Filled with 367 people, right? And those people, we're just going to give them numbers, right? We're going to dehumanize them a little bit. And we're going to have person 1, person 2, person 3, dot, 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 person 366, yeah, and then a person 367, right? Because that's what I said. I said we are going to have 367 people. Now, did you know that in this room of 367 people, at least two people were born on the same day of the year? Now, you might be wondering, why is that? Well, let's think about how many days there are in a year, right? There are 366, right? Don't forget about February 29th. Comes around only 4 years, but it's still a day. Still a day of the year, right? So if we think about the set of all days that are in a year, right? We have 1, 2, and this is the first day, the second day, the third day. I'm not going to label them by months and days. It's just first day of the year, second day of the year, third day of the year, and so on. So we'll say dot, dot, dot. And then we have all the way up until the 366th possible day of the year, which would be December 31st, right? So that is our set of days, right? And so now, if we think about a function that maps people, right? A function that maps people to days of the year, right? So let's do this. Let's do a little arrow, right? Let's say person 1 was born on the first day of the year. Let's make this very simple, right? So this is f of 1. Person 2 was born on the second day of the year, f of 2. And if we keep this map going, right? We keep this map going, dot, 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 blah, 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 for all 367 people, we see that the 366th person was born on the 366th day of the year. And then, well, would you look at that? We have run out of days of the year, right? So what do we do for poor person 367? Now, I'm not sure what day of the year person 367 was born on, but it was one of the days in the set of 366 days, right? So that means that 367, person number 367, will get mapped to, let's just say the last day. But arbitrarily speaking, person 367 is going to have their birthday on the same day as one other person in our set of 367 people, because the amount of days in the year is less than the amount of people we're looking at. So it has to be the case that at least two people were born on the same day. Are we starting to get a feel for this intuition? I would say by the pigeonhole principle, at least two people were born on the same day of the year, right? But now let's look at some like random math fact, right? This is gonna be I mean, to me this is totally random. Maybe to you it's not, but to me this is random. And we're gonna use the pigeonhole principle to show that this is true, right? So what I'm gonna say, let n be a natural number, right? Starting with our good old natural numbers, right? Then what I'm going to say, then there exist integers here. There exist integers a and b, but there exist a, b in the set of integers, such that 10 divides the difference n to the a minus n to the b. Now that is such a random fact, right? You can't tell me that's not a random fact. That's a random fact, right? But we could show that this is true by using the pigeonhole principle. How is that the case, right? Let's do a proof, right? Let's choose a different color, right? Let's look at a little light pink action going on. That's a little soothing to the eyes. All right, here we go. Let's say proof. We're going to let n be an arbitrary natural number, right? Let n be an arbitrary natural number. There we go. And this is a very short proof, by the way, so stay with me. Let A be the set of natural numbers. A is equal to the set, n to the 0, and let's not do n to the 0, let's say n to the first, n squared, n cubed, ... n to the 11th, right? So size of A is 11. We have 11 elements here, n to the first, n to the second, n cubed, blah, 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 n to the 11th, just to make that clear. So A is a set of natural numbers, and let me just say, like, it should be such that A is equal to that, right? Now, the ones digit, right? The ones digit of any element in the set A comes from the set B is equal to 0, 1, 2, 3, ... 8, 9, right? We can agree on that. Any number, right? That's not 0. Well, I guess 0 is included. In its one digit will either be 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9, right? These are just single digits that could be in the ones place, right? Thus, so the ones digit of any element in A comes from the set B, where it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Thus, by the pigeonhole principle, I always misspell pigeon. I don't know why, but I always stick a D in there. I don't know why. So thus, by the pigeonhole principle, if we define a function f mapping A to B, right? So f is going to map these elements n to various powers, 1 through 11, to ones digit placeholders, right, in the set B. So if we define a function f mapping A to B, then at least 2 elements in A will be mapped to the same element in B, meaning that these elements, call them A1 and A2, right? Call them A1 and A2, have the same ones digit, right? They'll have the same ones digit. Thus, their difference, that's not the right there, their difference has a 0 in the ones digit. Thus, 10 divides their difference. 10 divides their difference, right? Because if a number ends in 0, 10 will divide it. Thus we have shown there exist integers a, b, such that 10 divides n to the a minus n to the b. And that's the end of our proof. So does that make sense, right? So if we take an arbitrary natural number n, right? We say, all right, let's raise n to powers, right? We could have n to the first, second, third, blah, 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 n to the 11th, right? All of these numbers are going to end with either a 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9, right? Since we have 11 of these n's and only 10 possible numbers that can be the ones digit, We know that at least two of these n's, right, will have the same ones digit, right? And all of these n's, keep in mind, are being raised to different powers, right? Call those, I don't know, n to the a and n to the b. So we know that at least two of them will have the same ones digit. So when you subtract them, the ones digit will be 0, and thus you can divide it by 10. Does that make sense? I really hope that makes sense because that's the end of this video. So if you made it to the end of this video, thank you for watching. I really appreciate it, and I hope you learned something.